but he's also one of the founding members of a new nonprofit association specifically focused on HVAC design for Part 9 homes. And so yeah, so he's got great content to share. And with that, I'll turn it over to Mr. Dara to take us through.
Thanks, Ryan. Appreciate it. All those kind words you say about me. Okay. Now I think I've shared my screen. Can we see it?
It might just take a minute.
Yeah.
Just like last time.
Yeah, it took about 45 seconds last time.
Yeah,
so.
it's just loading. There we go.
There we go.
Okay, I'm seeing it. Okay, first slide. Advanced H. Here's the thing that I run into all the time, is that we don't build houses the way we used to anymore. It's almost completely different. The style, the structure, the windows, the insulation, everything, but we're still doing the HVAC the way we used to. We're still putting a big box in the basement and a furnace and air conditioner and like that. So the question is, why are we still doing this? And maybe we should be doing something different. I'm also here today representing HVAC Designers of Canada, which is, as Ryan mentioned, is a new association representing HVAC designers. And we have a lot of lofty goals about improving HVAC design in Canada and making it more accessible to everyone. That, you know, all houses deserve a good HVAC design, but a lot of times a good design is not accessible. It's difficult to find a designer, and so on. And there are associations, there are organizations, HRAI, and they provide services, but they don't represent designers. Of course, we know houses are more airtight, they have a better insulation, everyone has used to. The basement was unfinished, and that's where you shot gets down when to shoot bucks at the dryer. But now people expect living space in their basements. We have more windows, and we have different windows, different performance windows. But the windows let in the same amount of sunlight, but they let out less heat. We have unshaded windows and taller, larger windows. And we have lots more distributed internal gain. There's television in every room now. Certainly we didn't have a television at all when I was a kid. And all sorts of chargers and electrical devices all over the house. And houses are also more vertical in form. Urban houses are taller. We have less land, and it's expensive, servicing expensive, so the houses are taller. And also, where the step codes are coming. The homes we build now to meet code are much more efficient than they were 5, 10, 15, certainly 20, and certainly 40 years ago when I started. They're much more efficient than they were in the past, and they're going to get more efficient. I'm going to switch gears a little bit and talk about windows. And there's lots to do about windows. Out here, the bottom, the solar heat gain coefficient, and that means 0.54 means 54% of the sunlight striking the window comes in as heat. And then the other thing we want to look at is the U value, which 1 over U is the R value. So this particular window is not so spectacular, R3.2. Now, the old double glazed windows we had in the past were about an R2. But the solar heat gain coefficient was the same. If you take those numbers and the air tightness and you combine them into the energy rating, and it's up here, this is an ER31 window. The energy rating is a combination of several different things, including the U value and the solar coefficient. And there is a lot of variety available. There's a big spread of window configurations and ratings available. I find it's interesting to look at this spread And you look up top here, this is a really good window, R4.3, 0.51 solar heat gain, energy rating of 40. Now, if you look down here, on a solar control window, the R value is the same, 4.3, but the solar heat gain coefficient is only 0.2, and the ER rating is 21. So the ER rating, a large component of that is the sunlight coming into the window from passive solar heat gain. Look at what this means in a house. Here on the left, we have a high gain window. It's double OE argon, R4.5. It's a pretty good window. So 0.54. On the right, low gain window, it's triple, R value 5.9, pretty good. But the solar heat gain is 0.818, and this is going to restrict the amount of sunlight coming in the window, which may be really good if you have big windows facing west, so you don't overheat in the afternoon. But the heat loss of this house with the low gain windows goes down 4%. Now the heat gain, which means the size of the air conditioner, can be 25% less, but the energy consumption goes up. So here you have a tug of war. You have you want a window which doesn't let in too much sunlight, so your air conditioning loads don't go up. But if you start restricting too much, then your energy performance is going to suffer. And going down the road with energy modeling, we want higher and higher energy performance. So particularly with respect to windows, this is something you want to consider your HVAC design and your energy evaluation at the same time. And if that's not the same person doing it, then those two people should be talking to each other when that occurs. Something we notice is there's a real mismatch of heating and cooling loads that didn't happen before. Before, air conditioners more or less matched to furnaces, everything worked out. Nowadays, it's about 40% less heating than in a house the same size in previous years, but the cooling hasn't gone down much. And the other thing on top of that is that we now have updated load calculations, the F28012, for the same house compared to the older calculations. For the same house, we'll calculate the heating as being 20 to 40% less. And nothing has changed about the house, just the calculation procedure. And the cooling, 20, might change, 0 to 20% less. So you get the situation where 20 years ago, you had a particular house, put a 60,000 furnace in it, 48,000 load. It was fine. That's the industry normal, a 60,000 furnace in this house. But with all of the upgrades in energy efficiency, the load on this house has actually went down to 28,000. And when you factor in the more accurate calculation, when you do the actual calculation, you come out around 20,000 BTUs as the heating load for this house. So if you're putting in the 60,000 BTU furnace in this house, about the same size as you were 20 years ago, that furnace is probably 300% oversized.
Hey, Dara, just to
Yeah.
just to jump in quickly, are you able to comment on, is there an acceptable sort of oversizing? Like, you want to try to be as precise as possible, but like obviously you're dealing with different thresholds for equipment and things like that. So is there like an accepted range?
Not anymore. It used to be you don't want more than 40% oversize, but nowadays, two things happened. One is you don't have chimney connected furnaces anymore, so there's no off cycle loss. So there's no particular inefficiency connected with oversize. You have variable capacity furnaces, and a lot of people will tell you that, oh, I put in a two-stage furnace and it never went on high fire. Well, yeah, that's true, because the furnace itself was substantially oversized, so the low fire was probably exactly the right amount of heating for the house. And it would only go to high fire if, for example, you went away, you turned the temperature down, and you came back and you turned it up, then it might go to high fire. So it has a pickup rate. The other thing that's happening is that furnaces used to be sized on heat loss. Now the whole system is being sized on air conditioning load, because the air conditioning load drives the airflow for the system. If you look at the right-hand side, you'll see that glass and cooling starts to become much more important than heating. So in some situations, you'll actually have a bigger furnace than the house needs, but you want that size of furnace to support the air conditioning that the house needs. Is that a long answer to a short question, Ryan?
That's really good. It's really good.
But there is no, and it's, you know, some people who come at me and say, "Oh, oversize the problem, oversize the problem." I said, "Well, you know, you got a lot of houses that with in-floor heating, and they have a full-size furnace. So oversize itself is not a problem if it's properly controlled. If you have the right controls on it, you're okay." Let's look at, we'll talk about right sizing a little further on, and right sizing has a lot to do about having a good system, and what that means. Something I find interesting is how loads have changed, and this is the kind of load distribution we're getting now for houses. Like whole house heating is it's nicely distributed: glass, ceilings, windows, infiltration. All the loads come from different sources. But in cooling, really, there's only two things that matter, and that's your windows and your internal gains. The other stuff doesn't matter, because nowadays, all your walls and ceilings and everything are so much more well insulated than they were in the past. It's really not a factor in cooling the house. Other interesting thing is the basement. In the basement, most of the heating is about floors and infiltration, but the cooling, it's all about internal gains and glazing, depending on how much glass you have down there. Some basements don't have much glass. And what you can take away from here is that a lot of times you only need cooling in the basement when you have a bunch of friends over for a Stanley Cup party. Other than that, unless your brother-in-law moves in, you don't really need a lot of air conditioning down there. Main floor, same kind of story. Heating, the sources and needs are fairly well distributed. Cooling, it's all about the glass and the internal gains. And when you go to the second floor, same thing for heating, nice distribution, but the cooling, it's completely about the glass on the second floor. And I find it interesting to contrast that. If you look on the right-hand side, basement cooling's internal gains, not so much glass. Second floor, it's all about the glass. So you can easily see how in a lot of scenarios, the basement and the basement could need heating, and the upper floor could need cooling at the same time. In the spring, basement still a little coolish. Sun is shining in March, April through the windows, and you need cooling on the second floor. Now, I promised I'd talk about right sizing, and for me, right sizing is avoiding wasting dollars on oversized equipment, and particularly if you're going to be spending money on a heat pump, you don't want to oversize that puppy, because you're just throwing away money. It's not useful. The other thing is that you get smaller ductwork. If the ductwork is sized on the equipment, so if your equipment is too big, your ductwork is too big. But you can't reduce the ductwork until you reduce the equipment first. The other thing about right sizing and room by room is that now you know where your cooling priority zones are and where your heating priority zones are. And it allows you to move ahead and have a zone design so that you can cool the upper floor properly and heat the basement properly. And now, for topic, duct leakage, which I think does not get enough attention. But over the years, going out in the field, looking at problems, leakage is an issue. And most of the conventional system, most of the leakage is in the basement, and a lot of it is on the top takeoffs that no one ever sees. You go in, sometimes you go in the basement and you see all the transverse joints are nicely sealed, but no one sealed the top takeoffs. You can't see them, out of sight, out of mind, and that's where the air is leaking out. Now, the primary symptom of duct leakage in a Canadian home is stratification. That is, particularly in the summer, you don't get effective air conditioning on the second floor. Main floor could be okay. That's where the thermostat is. So it's going to drive to satisfy the thermostat, and the basement is too cold. How that happens is in winter, most of your leaks are in the basement. And so you have warm air leaking out, you need extra heat there anyways. The warm air rises to the floor above, makes the floor above warm, which is nice and cozy. And it can even rise up to even the second floor above can be made warm by warm air that leaks out in the basement. But if it's a room over a garage, it's not going to help much. And you switch over to the summer, leaks are still in the basement, but the cool air doesn't rise. And the floor above is not cool. The cool air settles down to the basement floor and makes it quite uncomfortable. And the second floor is above, they're not cool at all. And the rooms over the garage, well, they never were properly conditioned. So your basement is too cold. So you either rent your basement out as a meat locker and quit going to bed on the second floor, or do something about the stratification. And that could be solving. The other issue with duct leakage is actual air delivery. And there's still some, the old design procedures that we were using in the past assumed that all of the air went from the furnace or air handler to the end of the duct and none of it leaked out. It's not true. That never happened. The lowest leakage rate you can get is a sticky dust treatment on the ductwork. You can get down to less than 5%. So that means for a room over the garage, if you needed 100 to keep that room warm or cool, you need 105 to do it properly. If the sheet metal person is diligent and they use paint on sealer and tape and all the joints, they can get down to 5 to 15%. 10% is a normal target, so you'd need 118. The best leakage that you could expect without using sealant on the joints, that's good quality ductwork, tight fitting joints, it's about 20%. So you need 125 CFM. And we often see leakage in production homes in particular. And my experience is in Metro Toronto, where the HVAC installer is unionized, paid on piecework, and their objective is, and they're paid by the number of branches that they have to install in a house. So their objective is how many branches can they get to stay in the basement ceiling and not fall down the truck and off the job. So you get leakage rates that are very high, and at 50% leakage, and it's not uncommon, you would need exactly twice as much air to heat or cool that room over the garage properly. So as a consequence, rooms over garages are never properly heated or cooled. And that's your kind of painted on duct sealer works pretty good. Paint it on with a brush before you hang the trunks, and then do the bottom after the trunk is up. This is a high-tech system. Some people have heard of Aero Barrier, which is now coming on the market. This is kind of a sister company called AeroSeal, and they blow a kind of an aerosolized bubble gum into the ducts after the ducts are all hung. It's actually good because a problem solver. Can be done with ducts after the fact. Can be done with people moved in, furnished the house and everything. They can come along and older homes that have leakage problems, they can come and basically seal up the ducts. Quite an amazing process. Other side of stratification and advanced ductwork is zoning. And Natural Resources Canada is promoting zoning. And one of the benefits of zoning, particularly in air conditioning, is peak load reduction for electric utilities. And that, a lot of utilities, especially the ones in Southern Ontario, they hit a peak load in the summertime in air conditioning. But people who are air conditioning their basements, they don't have to. In fact, they're driving their air conditioners to try to get the upper floors cool. and overcooling the basement, and it's just a waste of energy. People who have zoned air systems are universally very happy with them. And if you look at the difference between conventional and advanced duct, the conventional has these large square boxy trunks in the basement, not adaptable to zoning. There's some custom fabrication involved for the trunk fittings, difficult to seal the takeoffs, especially after the fact because they're hidden. And all the floor supplies are really not very effective for air conditioning. And we'll get into some of that later. And there tends to be bulkheads and corner boxes for these big ducts. Advanced ductwork is using the same design rules, but just going at it differently. One of the differences is that it's zoned. Each floor has its own trunk coming off the air handler, so the trunks themselves are smaller. It's a lot more round ductwork, and but it uses common fittings, not straight T's, Y's, all those things. The round duct is easier to make airtight. So all the joints are accessible. The round duct is easier to integrate into the framing, and the return air ductwork is simpler, and we'll talk about that in a bit. And one of the things that some builders are offering is called zone-ready ductwork, and that is the trunks. The design is ready for zoning, but the actual dampers and thermostats and stuff are not there. And the HVAC installer has roughed in the wiring for the thermostat. So one, it doesn't drive the price of the house up that much, and it gives the HVAC installer something to upsell later on. Which, upsell the efficiency of the furnace anymore because they're all 96 or 97. So it's nice to have, if you're an HVAC installer, it's nice to have something to upsell or to go back later and say, would you like to upgrade to a zoned air system? Returns in every bedroom. I know a lot of people have heard, got to have a return in every bedroom. The fact of the matter is it's not required by a code or a guideline. Most of the bedroom airflows can be through a door undercut, and if you have groups of rooms like a master suite, then you can have a pass-through. And sometimes a master suite has double doors, so you have two undercuts to work with. And return ducts themselves are not that airtight, so for the bedroom in the back on the second floor, you're not going to get that much flow out of the return anyways, and if the plumber has to go through it, then you're not going to get much flow at all. And the fact of the matter is a good return can't compensate for poor air supply. When I look at heating and cooling comfort issues, the problem boils down to not enough warm air, not enough cool air going into the room. And if you can have the best return in the world, but if there's not enough warm or cool air going into the room, it's still going to be uncomfortable. So the newer designs were concentrating on having one big high return on the second floor near the ceiling, and that allows the system to take solar heat gain and internal gain and distribute it around the house and move it to a place where it's useful, like the basement. And having another big return low down to the basement floor, and does more or less the same thing, takes cool air off the basement floor and moves it to other areas of the house where it can be useful, especially in the summer. Door undercut can handle 60 CFM, 1-inch undercut 90, and that's about the airflow. A lot of bedrooms, 40 to 60 CFM is normal. And if the door undercut is not enough, then you can use a pass-through grill, which is simply return grills on two sides of a stud cavity, and lets the air out. Now, the other thing that
Dara,
yeah,
just to jump in on the zoning piece, we got a question here from a builder asking about how hard it is to add another zone for air conditioning in an existing house.
that's doable, and it depends on the house, but usually what you're looking at is if the ductwork is accessible in the basement, you need to go and put in motorized dampers basically on all of the branches. So a little more expensive and you need access to the ductwork because you'd have to, say if you have 20 branches on the main floor and 20 branches for the upper floor, you'd need to put in 40 dampers to damper so that you can turn off the main floor branches and open the upper floor branches and vice versa. And the equipment, if it's single stage equipment, you're going to want to replace it with dual stage and variable equipment. But a lot of people are going to upgrade their equipment anyways. So the zoning is an add-on to the upgrade.
Very good.
I have another talk about retrofit on retrofit zoning, and it helps a lot if you do energy upgrades to the house at the same time and then reduce the equipment size, because now it means the duct is oversized, and it's easier to zone the ductwork if it's a little oversized. It's not a day talk. Upper level rooms, in particular, now in the past, the HVAC systems were designed. Can someone please mute their microphone because I'm getting interference. Thank you. Everywhere in a house, heating was a priority. The HVAC system was designed. Some older houses we find it's difficult to get cooling on the upper floor simply because all the ducts were sized for heating. They were not sized for cooling. We need more air than for heating. So now the ducts are too small. The other thing is the floor supplies in front of the windows was because we had crappy windows and it was leaky over there. And when you sat beside the window, it was pretty cold. So you needed a heat register over there. But that's not true anymore. We have air sealing. The windows are much better. They're much more airtight. You don't actually need the heat register in front of the window anymore. And when you go to the upper floor, one of the problems that we run into in the field is the registers in the floor. You need cooling in the room, and in air conditioning, the air just kind of dribbles out the register, runs across the floor, outdoor, down in the hall and down the stairs, and it doesn't actually do the cooling that it should be doing in the room. So if you move the register high up in the room, then you get much more effective air distribution in the room, much more effective cooling, and much more effective ventilation because you get better air change in the breathing zone of the room. Now, to do that, you're not going to take a floor register and stick it in a sidewall. There are some very nice louvered registers available for a high wall, and they work very well. And here's this is a master bedroom with some of those louvered registers in them. And you can also get some pretty nice looking ceiling registers, and these are particularly effective because they spread the air along the ceiling boundary layer, and you get very good air distribution in the room. Now, I'm going to take a little segue here and talk about a pet subject of mine, thermostats. And what does a thermostat do? Well, there's the main thing it does is a control panel for the owner. Some people think that the thermostat heats or cools the whole house, and it all comes from this little thing on the wall. But no, it's a control panel. You control heating, cooling, system mode, fan circulation. Sometimes you control ventilation. Sometimes you control humidification or dehumidification. And the best location for that control panel for user access is usually the wrong location to sense temperature and humidity. So do yourself a favor, get a smart thermostat and with a remote sensor. So the thermostat can be in the right place for user access, but the remote sensor can be in the right place for controlling the house properly. And it basic thermostat located over the dimmer switch. The house is the house is comfortable when the lights are off, but you turn the lights on, the house is not comfortable anymore. framing and ductwork issues. New houses, fewer internal walls. And we now have manufactured joist systems, and most houses now, the framing package is designed by someone in another town using a computer with all their available joists and spans and so on. And joist direction change is a problem for ductwork. If the joists change direction on the same floor, or even if they change direction on the floor above, that's a problem for getting the ductwork to stay in the floor plate and not having it drop down to duct under joists. Joists that are not under studs, or studs that are not on top of joists, that's also a problem for verticals. Flush beams are a problem because the ducts have to duct down, floor level changes, and manufactured joists for long spans with 2x3 or 2x4 cords, and at 12 inches on center where you don't have room for a boot anymore, which is not really a problem if you're going high wall, but we have run into those problems. Joists with web openings are actually really handy, but sometimes it's too much to expect to put all of the ductwork up there. But the bottom line is that it's best to design your ductwork and your framing more or less at the same site. Same with the energy people and the duct design people. Better to have these people talk to each other and have these things designed, because what you don't want to do is have your house framed and then have your poor sheet metal person walk into the basement and say, oh my God, what am I going to do now? You should be able to have those problems sorted out before you get to that point. Next topic, the heat pumps are coming. The heat pumps are coming, and bottom line, you can't get to net zero without a heat pump. Done. But we have a lot of new technology in heat pumps. We have cold climate air source heat pumps and old heat pump. You know, when you below freezing, the capacity would drop off like a stone. But these new heat pumps, when you get below freezing, they have lots of capacity. And they're variable capacity, so it really suits a zone system. Very new air to water heat pumps. Used to be if you had in-floor heating, you were either stuck with geothermal or a boiler. But now air to water heat pumps are becoming available, and we're getting new products in all the time. We now have retrofit cold climate heat pumps that are designed. Someone's replacing their air conditioner and they want to upgrade to a heat pump. There are some pretty high-tech units, variable speed units, that are designed to just replace the air conditioner. One of the ones that's new on the market will work with any TXV coil. Doesn't matter. It could be a heat pump and a Mitsubishi coil. They're not fussy. Did I just drop the audio here? Am I
Yes, you
back?
Yeah,
did.
just for a
You
second,
did for a
Derek.
second.
Okay, good. Did you guys miss talk about the last thing I said was the new retrofit heat pumps? You don't need to match the coil and the outdoor unit. You don't need a Mitsubishi coil with a Mitsubishi unit. You can have one of these new variable speed cold climate outdoor units, and a good TXV coil made by anyone will work.
And they'll still achieve, Derek, quickly though, and they'll still achieve the same COP as a match system?
Yes. Well, they're working on the matching, but there's a lot of matching going on. And you can tell that, if you have a 2-ton outdoor unit and you match it with a 2-ton coil, you get one performance, but if you match it with a 3-ton coil, you get better performance. So they're new on the market, and they're working on the coil matching now, and they're going to have a bunch of matches to commonly available coils.
Great, thank you.
But okay, back on track. Heat pumps. What is a heat pump? Heat pump is an air conditioner backwards, basically. And it brings heat from the outside, even at cold temperatures, and at significant energy savings over straight electricity alone. Heat pumps lose capacity and efficiency as the temperature goes down. And in a lot of homes, and we'll see this further on, you may require backup or supplemental heating. If the home needs an air conditioner anyways, there's not a big incremental cost for an air source heat pump. If the home is not planned to have an air conditioning or you don't have ductwork, then there can be a significantly higher initial cost for a heat pump. There is a particular type of heat pump system, and that's add-on to a gas or propane furnace. It's called a hybrid heating system. In order for this to be cost effective, if your base fuel is natural gas, you need a utility program that gives the homeowner cheap off-peak electricity, because right now natural gas is about 1/3 the price of electricity, so it's not worthwhile. You're not going to save anything by putting a heat pump on a gas furnace if that's what you're trying to do. You may get situations where, in order to meet your energy targets, that would be the right thing to do. And you know, depending on the energy supply for your electrical utility, could be a lower carbon solution. As carbon taxes kick in, this may be the way of the future. But right now, most areas, you need a utility off-peak electrical program to make it work. When you talk about air conditioners, the performance factors are EER and CER. Most air conditioners are rated by CER. The national minimum is CER 13, and higher CER number better than lower ones. And you know, the highest ones we see up around 19, CER 19, CER 20. Heating performance for heat pumps, COP is the coefficient of performance, is instantaneous, basically energy in, energy out. And HSPF is the heating seasonal performance factor. And in BC, lower mainland, the HSPF is region 4, because HSPFs go by region. The rest of Canada is region 5, is colder, but lower mainland BC is region 4. So when you're looking at the literature, looking up the HSPF for a heat pump and comparing it to another one, you want to make sure you're comparing the same region. A little look at efficiency. Baseboard heater COP is 1:1. It's 100% efficient. A regular air source heat pump, about 2.5 COP, HSPF about 8, and could run down to -15. A cold climate heat pump, as compared to a regular heat pump, COPs about 3, higher COPs, more efficient, and better heating season performance factors. And all of these air conditioning. Heat pumps and air conditioners, you'll see them as ductless mini splits, very popular for retrofit. You have an outdoor unit and you have an indoor unit, and a lot of times I compare it looks like an alien birthing pod stuck to the wall in your room. You see them a lot in Europe. You need to cover a house, you need multi-heads or a multi-head heat pump or several heat pumps. You may need supplemental heat in on-grade or walkout rooms. You still have to provide ventilation, and these won't provide ventilation for the sleeping living room, so you have to have a ventilation system to do that. They're not good at moving around the internal solar gains from one area to another, and humidification and dehumidification are also issues. Central heat pump is the same kind of technology, except now instead of having a head mounted on a wall, you have a regular air handler. Right now, a lot of the central systems available is you have to match the air handler with the outdoor unit by brand. The other type that we were talking about is a hybrid heating system where you have an air source heat pump matched to any type of furnace. A gas furnace is a propane furnace, very popular. You have an indoor case coil and your outdoor unit. And recently on the market, we have cold climate outdoor heat pumps that are suitable for retrofit. But it doesn't have to be the furnace brand and the outdoor unit brand don't have to be the same. I've noticed a lot of consolidation in the HVAC market where the manufacturer wants you to get their air conditioner and their furnace and their thermostat, so you can't mix and match components. NRCan has recently published air heat pump sizing and selection guide, which is very handy. And a little deeper look at that. What I was talking about before is this is the heat loss for a house. When it's warm, you don't need heat. When it's cold, you need a lot more heat. And that's basically the curve. Warm to colder, you need more heat. But heat pump goes the other way. The colder it gets, the less heat you get out of the heat pump. So there's going to be a crossover point, and that's what we call the balance point. Now, the green line and the orange line here, those are regular heat pumps. The orange one, 3 times a little bigger than the 2.5 ones, so you get better performance balance point. And the red line is a cold climate heat pump, so it does better when you get below freezing. There's the inverter ramps up and the vapor injection comes on, you get better performance at low temperatures. So the balance point is at a lower outdoor temperature and it covers more of the house heating requirements. In terms of controls, this is the old style traditional method of control for a heat pump. And that is when you get to the balance point and the heat pump can no longer carry the whole heat loss of the house, the control system turns off the heat pump and then turns on the backup, and that's it. Below that point, the heat pump has nothing to say about it. That's the old style control. Newer style control is what we call hybrid operation. And what happens at the balance point when the heat pump can't provide all of the heating requirements of the house, then the backup comes on, but the heat pump and the backup share the load of the house. If you, for example, if you had a gas furnace with a heat pump, then the heat pump would be on stage 1, the gas furnace would be on stage 2. So if the heat pump would operate when it's cold, if it couldn't keep up, then it would turn off, switch over to the gas furnace for 10 or 15 minutes to bring the house up, and then go back to the heat pump. So you cover a much larger portion of the energy requirements of the house covered by the heat pump. It's not just, anyone who does energy evaluation will say when you put the heat pump in unrestricted mode, you get a lot more energy savings. Now, this is where we're going. What is happening is, we mentioned before, this house here, this at a 50,000 BTU per hour house at the design temperature. But what's happening is the heating load of the house is coming down. So, and especially in lower mainland BC, it's entirely realistic that the air source heat pump could cover the entire load of the house. Now, so, well, you need a bigger heat pump for that. Well, we still need a certain size heat pump to cover the air conditioning load of the house. So if the heat loss of the house comes down, we're not going to be reducing the size of the heat pump because we still need that size of a heat pump to cover the air conditioning. So this is where we're going. When we get to the higher steps, we get to net zero, we're going to get situations where the heat pump covers the whole load of the house. And we're doing these now, the higher energy performance towns, so on. The heat pump can cover the entire load of the house, not an issue. If you look at selection, I talked a bit about that before. If you're talking about selecting a heat pump and you want least incremental cost, you just size the heat pump on the now, if you're interested in the energy performance pump, you may increase the heat pump size a little to get you better heating energy performance. But it's not going to impact your air conditioning because it's going to be a variable speed unit, so it's not it's only going to cool as much as it needs to. And if you're high step code or net zero type home, you're going to size the heat pump to cover your full heat loss. But your air conditioning is going to be covered. And in 99% of the cases, the air conditioning is going to be covered.
Hey, Dara, I'm just
Uh,
doing a little time check. We're at 9:20. And so we were
Okay.
on our schedule at 9:30, we're going to go to questions. So just,
Okay.
just a little nudge.
So I ran through that a little quicker than I had planned.
Wonderful.
Can we go to questions? Can we go to questions now?
Hey, Dara, I'll jump in really quickly here.
Yeah.
You know, when we saw the presentation that you ran through with us, the co-host there a few days ago, one of the things that jumped out for me, anyways, was you know, cold climate heat pumps aren't just for cold climates. And so I'm just wondering, you know, that was a real realization for me, and I guess for those building in climate zone 4 in Southwest BC on the southern half of Vancouver Island, a cold climate heat pump could be, you know, just as viable as a solution as another brand of heat pumps with maybe a different sort of performance range, optimal performance range in terms of climate. Just wonder if you comment on that.
Yes, definitely. I mean, you should be, especially because since Natural Resources Canada has their heat pump guide. You know, if you're interested in the energy performance, you should sit down with your energy evaluator and the performance of the units you're considering, and check it out. See the cold climate heat pumps, as shown in this slide, do provide better. I mean, most of the heating occurs at lower temperatures, and they do provide better performance, higher COPs, higher capacity at the lower temperatures. No, yeah, you don't need the heat pump to go down to -30, but when it gets below freezing, and you know that's where a large chunk of the heat loss and load occurs, that heat pump is going to be a better performer. The other thing I'm going to say is some of the mainline heat pump manufacturers, Carrier, Lennox, Rheem, Rudd, if you look at their newer variable speed heat pumps, they have very good cold weather performance. Whereas if you're getting their regular off the shelf heat pump, no, the cold weather performance is not very good. But you know, I would say that like the Highline Carrier, you know, Green Speed, that qualifies as a cold weather heat pump, really.
Really good, Dara. We had some questions come in through the chat, so maybe I'll moderate a few of those to you, so that you can address them here. So, first question is there a and this came in from my friend Mike Rugamer, is there a unified term of measurements that heat pumps get tested at, or is it simply manufacturer specs per their test? This is a very good question.
It's a very good question, and it's very timely, because traditionally heat pumps were tested at 47 degrees Fahrenheit, and optionally at lower temperatures than that. But you know, the standard HRI test points that are reported by manufacturers are not particularly usable. They don't show the cutoff points. They don't show the lower temperature performance. And even manufacturer to manufacturer, if you look at their literature, they're not comparable. So there is a new CSA heat pump, cold weather heat pump. There is a new CSA heat pump testing standard, and NRCan and other people are working to get that implemented and get the manufacturers to test to it. This is a work in progress, but it is really a need in the industry to have that information hole filled with the right information that we need to design our homes properly. And NRCan is spending a lot of time on it. They have a cold weather heat pump testing lab set up in Ottawa. And they're actively testing heat pumps. I did some of the design for that. They're actively testing heat pumps. It can go down to -20 in the middle of the summer. And they're also doing field research. I have 2 of their field research jobs testing cold climate heat pumps in the field to see what the actual performance is when it gets cold. But we are behind the industry. The heat pump manufacturers, the reporting standards are behind the needs of people who are using heat pumps right now.
Yeah,
I go back 30 years to something I was highly involved with, and that's CSA C439 and the HVI standard, which is testing for heat recovery ventilators. When I first started in the heat recovery ventilator industry, it was people could make up their own performance standards. There was, but industry, thank goodness, got together, sat down, and came up with meaning performance for HRV that we all use now. It's universal, and they were good enough so they didn't have to be upgraded. But this is not the case for the heat pump industry. So it's a work in progress.
Okay. Yeah, that's really good. Yeah, and I've seen that standard was just published, so they're pushing for the manufacturers to standardize the testing procedures, and then everybody will be reporting out apples to apples, basically, right?
Yes, and meaningful numbers when it gets cold. Right now,
Yeah,
you don't
exactly.
have meaningful cold weather numbers, and different manufacturers will report different numbers at different temperatures.
Okay. Question here around I guess how do the senators around, how do you convince homeowners to go all electric when the capital and operating costs of equipment really push you towards gas type solutions? So very small question there for you.
And not only homeowners, but townhouse developers as well. We're talking about large projects like 30 units, 40 units, and they're all getting installed with gas with rough-in options for future air conditioning.
Very good.
Yeah, I'm sorry, I'm not a marketing guy. So I really don't. I can tell you that one of our clients is a townhouse developer, and he was doing Energy Star townhomes, and they were very successful. And his next townhouse development is going to be net zero. And he found it was quite easy to do with the townhomes once he got his performance up. And he does not have to bring gas to the site. So he pocketed that money that he would ordinarily have to give to the gas company to bring in their distribution lines. So that's the way he's going. He believes his research has shown that the young people buying these townhomes, they want the energy efficiency. They really like net zero, and the air source heat pumps that he's using will cover 100% of the load. He was considering geothermal, and there was a program that Enbridge Gas is offering in Ontario where they realize that with the heat loss going down on new developments, they're putting distribution lines in, and they're not getting a return on investment because people aren't using as much gas. There may be a 40,000 BTU furnace there. With the low heat loss and it's not using as much gas as it used to. So if you go at a high level, they're really they finance infrastructure through revenue. So they looked at it and said, well, we will provide the geothermal loops for your development, and we will charge back the homeowners so much a month for their access to the geothermal loop, much the same way that they would get charged for natural gas. And a lot of the bill of the natural gas is not for the gas itself. It's for the infrastructure and the delivery of gas. Same with your electrical bill. So the Enbridge, as a gas company, was looking at that as a new way of doing business. Now, this particular developer, when they looked at the dollars and cents, said, no, actually, I'm better going off with an air source heat pump because I can do it. And this is in Southern Ontario. So I don't know. He didn't, go over what his marketing was on that, but you go to higher policy levels. That's one of the objectives of carbon tax. And one of the problems with the carbon tax is people use natural gas, so the natural gas producers want to keep producing the same amount of natural gas, so they keep lowering the price. It's kind of it's a sadist and masochist problem.
Yeah, the only couple things I would add is like there's now an equivalency in terms of incentives around going with all electric through the province's Clean BC program to help facilitate more electrification and heat pumps. And then actually Raul made one of the builders here made a good comment about as you get to the higher tiers of the step code, the mechanical energy use intensity figure, which is a metric within the step code, gets more difficult to achieve with gas type solutions. So from a regulatory standpoint, requiring higher steps makes it harder to use those types of solutions.
I mean, with fair number of net zero and for we found in net zero, the gas, if you have gas or propane, is very useful, but for a backup generator, not for heating the house.
Dare, the section on duct leakage I thought was really, really good, because I don't think that's a real concept that's fully understood within the building industry. Is there some practical things that you would recommend for builders on how to manage like the workmanship and their sub trades to know that, like, when the sheet metal work is done, they've got a good finished product, that the CFMs in the back bedroom are actually going to be there? Like, I know you can do duct blasting and all those kinds of things, but like, what are some things that builders can use as like tips to like hold some accountability of their HVAC sub trades?
Without actually doing duct leakage testing, it's difficult. But if they take the time to walk with their subtrade, if in conventional ductwork, to walk with their subtrade before when they're hanging the trunks, because they're going to assemble the trunks on the basement floor. They're going to cut in their takeoffs, and then they're going to hang them up. And at that point, someone with a pot of duct sealer and a brush needs to go around and seal every takeoff, because tape is no good for sealing those takeoffs. It's just a thing that if the HVAC, if your HVAC stub says, oh yeah, my ducts are sealed, a walkthrough afterwards, looking up at the ceiling, is not going to tell you whether the ducts are sealed or not. And also tell his people in the field, okay, make sure you seal the ducts. And you run across the attitude, hey, I'm a trained sheet metal mechanic. I'm not a painter.
Yeah.
I'm not doing this sissy stuff. So that for me, aside, if you're not going to test, then it needs to be done at that level to make sure that those takeoffs and those trunks are sealed before they're hung in the basement ceiling. And if the next step beyond that is to simply say to your HVAC installer, the ducts are going to be tested, and if there's more than 10% leakage, you're going to have to fix it, and we're going to come back and test again. At that point, it becomes economical for the HVAC installer to say to his people, okay, do good ductwork, nice tight joints, don't bother with the sealing. We're going to bring the AeroSeal people in when you're done, and we're going to seal it. And the AeroSeal people use the same test results that you would get with the duct blaster.
Yeah.
So we accept their test certificate as just as good. So in fact, the HVAC installer is now further ahead because one aeroseal is less than 2 air leakage tests. If he fails the first test and has to pay for the second one, he's just paid for his aeroseal job. So he might as well tell his guys to don't mess around with the tape and the paintbrush, silly paintbrushes. Put it up, do a good job. We'll have the aeroseal people come in, and we're done, and everybody's happy.
Okay. And then
you know,
just one last question. Oh, go ahead.
Yep.
One last question.
It is.
Yep.
It is true. In the big picture, duct leakage is the skeleton in the closet.
Yeah.
No
Agreed.
one wants to. Industry for years and years, no one wants to admit that the ducts are leaky. And up until about 5 years ago, we could tell people that the ducts leak, but we had no solution. We didn't know what to do after that point.
Yeah. Okay. Actually, this is a good question. Just came in. I think from Scott Silverthorne and Barb. They were asking for a bit more of elaboration on the point about oversized equipment is not a problem with appropriate controls. So were you referring to multi-stage furnaces and what controls could be applied if oversized equipment has been installed? Yeah, it's the modulation and things, right?
Yeah, I mean, if it's oversized single stage equipment, yeah, you got a problem.
Yeah.
It's and it's more of a problem with oversized single stage air conditioning than it is with heating, because you know, and yeah, sometimes we get this situation where the ductwork has been designed for the house. The HVAC installer in his usual practice walks through and says, oh, I got a 5-inch here and I got 2 5-inches in this room, and we'll use 2 6s in this room. And then the furnace gets oversized. Now the ductwork is too small. That's another problem.
Yeah.
It's not really oversized, just the ductwork is too small.
Okay. Well, Dara, thanks again. Like that was a really great presentation. Lots of yeah, if it's really quick.
Yeah,
go ahead.
I'm a designer and a builder, and I installed geothermal as well as heat pump. The only thing I haven't installed yet, which recently we have to do it eventually, is 100% heat pump electrical. How's the heating system works here, and what type of heating system we have here in this type of situation? Is it going to be electrical? How can you explain me how that works?
Well, if it's a central system, then an air source heat pump with a matched air handler has the electric heating coils inside the air handler, and the system controller controls the heat pump and the backup electrical coils. So it will bring on only as much electrical backup heat as is needed. For example, below, say there's 15 kilowatts of coils in the air handler, you're below the balance point, the heat pump can't keep up, it'll bring on 5 kilowatts. It won't bring on the full 15. It would only be in an emergency heat situation, if your compressor failed or something, that it would bring on the full 15. So for those types of matched systems, the control is smart enough to do that.
So what is our main heating source in the house?
The heat pump.
Heat pump.
So it's going to be a unit outside the building. We don't need any heat source inside the building.
Not sure what you mean, but if it's electric backup, you need the electric heat sources in the building. But it's
so that's my question. What is the heating source?
All electric. Well, it depends whatever they're using to generate the electricity with. Could be hydro. I don't think you have any coal plants left in BC. We got rid of our coal plants here. But in Nova Scotia, it's a problem because a lot of people heat with electricity, and a lot of the electricity is generated with coal-fired generating plants.
No, my question is, what is the heat source in the house?
Is the use of the heat pump.
Yeah,
So
Yes. We gotta wrap up. I'll happily follow up with you afterwards to talk about like heat pump and backup power and all that kind of stuff if you'd like, but we got to move on. So we're going to the second part of our session. Shannon, do you want to jump in with just the directions to folks? I know you put some stuff in the chat, but.
So I'm really sorry for anybody that might have had troubles logging in. We'll look into that for next time for sure. What we've done is created separate meeting rooms for municipalities for both New West and Richmond. There is no breakout room for Surrey today. In order to receive your credits, please log into the appropriate municipal meeting. If you look to your right in the chat function, it has a little bubble. There'll be links to either Richmond or New West. And we'll be doing breakout rooms there. We'll take about a 3-minute bio break so you can hit the bathroom or grab some water, and meet you on the other side.
Yeah, and the only thing I'd add to that is just that this whole session has been recorded. So some folks joined kind of midstream because of some technical issues with, I guess, the link that may have been in Eventbrite to join the meeting. So you'll be able to view the parts that you missed from that video when we send out the link.
And one last thing, if you have any problems copying the link in the chat, all the attendees received a message from Eventbrite that also has those links. Thanks, everyone.
All right, thanks everybody. Thanks again, Dara. That was really terrific.
Thanks, guys.
Bye now.
Nice to talk to everyone. Nice to meet everybody.
Thanks, Dara and team. Thanks.
See everybody. Bye.